Hello and welcome to DrugsPlus. Whether you're here for exam revision or just general interest, I hope you find this video useful. If you do, please give it a thumbs up and subscribe for similar content coming soon. In this video, I'm going to introduce my first series, which is all about treatments for type 2 diabetes. The prevalence of this condition is rising rapidly in the UK and currently accounts for 10% of the NHS's budget. That's £10 billion every year. And this isn't only an issue in the UK. Around 9% of the total global population are believed to have the condition, so it's no surprise that therapies are constantly being developed. So what actually is diabetes? Islets of Langerhans are small patches of endocrine tissue in the human pancreas. They contain alpha cells, beta cells, and delta cells, among others. When our gastrointestinal tracts are empty, usually periods above 3 hours after meals, alpha cells secrete glucagon. Glucagon acts in a wide range of tissues in the body, all with the aim of ensuring blood glucose concentrations don't get too low. These effects include inhibiting the uptake by bodily tissues, as well as the breakdown of storage molecules to generate glucose. However, when glucose is being absorbed from the gastrointestinal tract, usually shortly after a meal, beta cells are stimulated to secrete insulin. As well as inhibiting the secretion of glucagon and therefore inhibiting all of its effects, insulin acts in a large variety of tissues, all working to reduce blood glucose concentration. These effects include increasing glucose uptake into tissues, as well as increasing the production of storage molecules. As you can see, these two hormones have opposing effects and together produce blood glucose homeostasis. However, in type 2 diabetes, the insulin arm of this process is diminished. This can be caused by dysfunctional beta cells resulting in increased or reduced insulin secretion, or reduced insulin sensitivity in peripheral tissues, or usually both. So, when blood glucose concentration is elevated after a meal, glucose enters beta cells via glucose transporters. It then gets metabolized by glycolysis, the TCA cycle, and oxidative phosphorylation, producing adenosine triphosphate, or ATP. This ATP then binds to and blocks ATP-dependent potassium channels. This channel usually mediates a constant potassium efflux, so when this is blocked, the cell becomes depolarized. This causes voltage-gated calcium channels to open, facilitating a calcium influx. This calcium works both directly and via secondary enzymes such as adenylyl cyclase and phospholipase C to stimulate the exocytotic release of insulin. That is the process of glucose-dependent insulin secretion. Insulin then goes on to activate insulin receptors on target tissues. The insulin receptor consists of 2 alpha domains and 2 beta domains. The alpha domains contain the insulin binding sites, and the beta domains contain the tyrosine kinase. When insulin activates a receptor, the tyrosine kinase domains become autophosphorylated and therefore activated. These domains then recruit insulin receptor substrates 1 or 2, which act as scaffold proteins upon which downstream signaling complexes can form. This produces 2 series of effects, the growth-promoting effects and the metabolic effects. For its growth-promoting effects, the IRS molecules bind to the SH2 domain of GRB2, which forms a complex with son of sevenless, or SOS, in order to promote the binding of GTP to the monomeric G protein RAS. RAS-GTP binds to and activates RAF, a MAP kinase. RAF phosphorylates and activates MEK, a MAP kinase, and MEK phosphorylates ERK, a MAP kinase. ERK is then imported in the nucleus via an importin, where it phosphorylates various transcription factors which control growth. But these effects don't really have anything to do with diabetes. They're more to do with the metabolic effects. So, for those effects, the IRS proteins bind to the 85 kilodalton subunit of PI3 kinase. This induces a conformational change in the 110 kilodalton subunit, mediating its activation. This catalytic subunit phosphorylates phosphoinositol molecules at position 3, producing phosphatidylinositol trisphosphate, or PIP3, which recruits PDK via its plextrin homology domain. PDK phosphorylates protein kinase B, or PKB, which mediates the metabolic effects that I spoke about previously. So, the pharmacological treatments for type 2 diabetes, which I will talk about in subsequent videos, include SGLT2 inhibitors, which increase glucose excretion, alpha-glucosidase inhibitors, which decrease carbohydrate digestion, GLP-1 analogues, dpp-iv inhibitors, sulfonylureas, all of which enhance insulin secretion, and metformin and TZDs, both of which increase insulin action. Thank you for watching this video. If you found it useful, please give it a thumbs up and subscribe. I'll be back with more pharmacology videos soon.